Let's start with exercise number 6, a relatively simple polynomial function where y equals x to the fifth minus 5x. And we'll just kind of run through the special features from this section. First, let's look for the domain, since that governs pretty much everything else about the function. It tells us which x values are even under consideration as we go through these various other points. This is a polynomial. It is clearly defined for all real numbers, so the domain is R, the set of all real numbers. If you are in a situation such as WebAssign where you might be asked to write the domain in interval notation, of course, that is the interval from negative infinity to infinity. But for handwritten purposes, any legitimate set notation is fine here. Next, let's examine intercepts. It's usually easiest to find the y-intercept, since this is simply the point on the graph when x equals 0. Right, we want to know where the graph crosses the y-axis. On the y-axis, x is equal to 0, so we can simply set x equal to 0 and see what we get. In this case, y is also 0. So the origin, 0, 0, is the y-intercept. Let's look now for any x-intercepts. This tends to take a little bit more work, intercepts, because now we're looking for where this crosses the x-axis. That would be where y equals 0. So we would have an equation to solve. To get some general information out of this, rather than just directly plugging that in, because it's, we don't know what all we might need. Let me pop to another copy of this, and let's go ahead and factor y. Sometimes it's nice to have our function in more than one form. If we pull out an x from that, we see that we have x times x to the fourth minus 5. And depending on what we need with this, we might want to factor further. So we could say, okay, well, we can treat that as a difference of squares. This is x squared minus the square root of 5 times x squared plus the square root of 5. And continuing to factor, we have x times x minus the fourth root of 5 times x plus the fourth root of 5. This is just factoring this term here, x squared minus square root of 5. Treat that as a difference of squares. We can pull that apart like so. And then we still have this last factor here of x squared plus the square root of 5. Now that isn't strictly necessary in this particular problem, because we can actually solve this pretty quickly, especially from this first one. But for some purposes, it might be nice to have the full factorization. So I just wanted to show you how we could do that. But really focusing on kind of this first line here, these early factors, if we consider where this is equal to 0, we see that if x equals 0, we get y equals 0. And also, if x is one of the fourth roots of 5, we can also see that from this full factorization here. X squared plus 5 has no real zeros, but we have these three other factors with zeros of x, fourth root of 5, negative fourth root of 5. So for x-intercepts, we have 0, 0, and we also have plus or minus the fourth root of 5, 0. Don't forget that intercepts are points in the plane, so they should, in principle, always be listed as ordered pairs. In some circumstances, you might see just the y value or just the x value listed as a shorthand, but if we want to be precise, we have actual locations here. For graphing purposes, we would like to know how big this fourth root of 5 is. We know it's going to be bigger than 1, but less than 2. Being more precise than that might take a little bit of work if we were to do this by hand. You might be better off trying to estimate square root of 5 and then the square root of that. But if we have a calculator on hand, we can see that this is approximately 1.5, plus or minus. I'll just jot that down there for future reference once we get down to the stage of graphing. Next up, let's examine symmetry. And I'm just kind of running through things in the order that the book does. For the most part, the order doesn't actually matter that much. You probably want to do certain things earlier than others. Finding the domain should be very early on your list, for instance. Whereas looking at things like concavity being a second derivative, that would come later. But for the most part in between, there's a lot of flexibility in terms of what order you do things in. But like I said, I'm just following the book's order to make sure we don't miss anything. So symmetry, we have three types that we talk about. There's even and odd symmetry. These involve reflectional symmetry over the y-axis or the origin. And then there is the translational symmetry that we get of a periodic function. About the only periodic functions you've seen so far would be trigonometric functions. We don't have trigonometry here, so we don't expect to have periodicity. But we do have a polynomial, which means that it might be even or odd. Even and odd symmetries are named after the power functions that have those same symmetries. And we see that this polynomial consists only of odd powers of x, so we expect the symmetry to be odd. If we want to be certain of that, which we should do until you've until you've done a lot of work with these, let's let f of x equal y. We haven't actually had given this a good name yet. It's just been y. Let's give it a function name as f of x. And we can check the symmetry algebraically by taking f of negative x and looking at what happens when we simplify it. So we would have negative x to the fifth minus 5 times negative x. And simplifying this, negative 1 to the fifth is still negative 1, so we have negative x to the fifth. This becomes plus 5x. So we've simplified this. And the first thing we want to ask ourselves is the question, does this equal the original function? We check, and no, it does not. If it did equal f of x, then this would mean that we would have even symmetry. It doesn't, but now let's see if it's the negative of the original function. If we factor a negative out of this, we have x to the fifth minus 5x, and that is the negative of f of x. Since f of negative x equals negative f of x, that means then that we do in fact have odd symmetry. That's the algebraic characterization of this. So, my rough sort of heuristic assessment of this turns out to have been correct. We do have odd symmetry, so we will have symmetry over the origin, which you can think of as reflectional or rotational. In 2 dimensions, those are the same thing if we're reflecting over a point. So that could be useful later to make sure. We want to be thorough, so we don't want to use that as a shortcut probably, but that could be useful later to check and make sure that everything has come out correctly, confirming that the graph does indeed appear to have that sort of symmetry. Let's now think about asymptotes. Asymptotes. There are 2 separate kinds of asymptotes we consider. One kind is vertical asymptotes, which generally occur when there are discontinuities of some sort, but polynomials are continuous over the entire real line, so we expect to have no vertical asymptotes. We can also consider the asymptotes that we get from end behavior. These might be horizontal or slant or even nonlinear, but a polynomial will not have horizontal asymptotes unless it is constant. A non-constant polynomial will not have horizontal asymptotes. A nonlinear polynomial will not have a slant asymptote. Basically, if you have a polynomial, the simplest function that describes its end behavior is that polynomial itself. So, we don't really have asymptotes to speak of. Any other function that this would be asymptotic to would be more complicated. So let's say none for our purposes. Let's see, no asymptotes. Next, we want to examine where this is increasing or decreasing. So let's come back over to this extra scratch page that I have, and we will consider taking its derivative. Increasing and decreasing is due to the derivative. Y prime is equal to 5x to the fourth minus 5. This is obviously easier to get from the original polynomial version as opposed to one of the factored forms. So if we want to know where this is increasing or decreasing, we want to find the critical points. And the critical points happen when this is either undefined or 0. This is a polynomial, so it's never undefined. So let's set that equal to 0. we see we have 5 times x to the 4th minus 1 equals 0. And you can look at this and hopefully see that x equals plus or minus 1 is the solution we get. You might, of course, also factor that further. We have x to the 4th minus 1, so you can factor that as a difference of squares, much like we did above. And one of these is a difference of squares, so we have x minus 1 times x plus 1 times x squared plus 1. X squared plus 1 is irreducible over the reals. There are no real solutions for that, no real zeros. But x minus 1 and x plus 1 give us the zeros of plus or minus 1. These are the two real fourth roots of 1. So we can make a little sign chart. We have -1 and +1, and we want to figure out where y prime is positive or negative. And there are a few ways you can do that. You could use test points, or you could just look at the end behavior. We see from this 5x to the 4th that it should be positive on the two ends and negative in between. You can confirm that if you pick 0. If x is 0, we get -5, which is negative. So we see that our function increases here, decreases here, and increases there based on the signs of what we have. So, let's see here. Our function is increasing on the intervals from -infinity to, I believe I said -1, -infinity to -1, and from 1 to infinity. And it is decreasing in between from -1 to 1. So we know where that happens. Let's consider extrema. At this point, we have basically already done the first derivative test, right? We've found critical points, we've checked the first derivative, so we can see that there is, following the contours of this, we can see that there is a local maximum at -1 and a local minimum at +1. So we have a local maximum at when x equals -1, we'll come back to that in a moment, and a local minimum when x equals +1. We want to know where exactly those points are, so let's evaluate these. Plugging -1 into our original function, we have -1 to the 5th is -1, minus -5 is +5, so we get 4. And similarly, plugging in 1, we have 1 minus 5, giving us -4. So we have these local maximum and local minimum positions there. That takes care of extrema. All that's left now is to look at concavity and inflection. So for that, we want our second derivative, y double prime. Here is y prime, 5x to the 4th minus 5. Y double prime looks like 20x cubed. This is equal to 0 only at 0. When x is greater than 0, this is positive. When x is less than 0, this is negative. So that means we have concave down on the left and concave up on the right. Left and right of 0, I mean. So, let's see. Concave downward on the interval from -infinity to 0. I think it was down on the left. Yeah, it's down on the left, up on the right. And concave upward on the interval from 0 to infinity with an inflection point because it switches concavity at a point that is in the domain of the function. When x equals 0, and we've already evaluated, we know that y is equal to 0 there. So that covers all of the main points raised in this section. You can see there's a lot of them. Let's go ahead and try to develop a rough sketch of this thing, what approximately it might look like. Take an x-axis and a y-axis. We always need to make sure to mark out an appropriate scale. So let's see what matters here. As far as y values go, we need to cover up to plus or minus 4 for those extrema. X values, we have plus or minus 1.5. So let's take y going up to 4 and down to negative 4. Hopefully that's approximately symmetric. I'm not too concerned with the details. And for x, let's go up to 2 and down to negative 2. And running through, we saw 0, 0 was important for a lot of things. It was one of our x-intercepts, it was our y-intercept, it was a point of inflection. We had that showing up a lot. We also have x-intercepts located at approximately plus or minus 1.5. So around here and here, give or take. What else do we have? We have a local maximum at negative 1, 4, and a local minimum at 1, negative 4. So we have negative 1, 4 is a maximum. 1, negative 4 is a minimum. We have concave downward on the left half, meaning it opens downward there. Concave upward on the right half. And we had decreasing from negative 1 to 1 and increasing elsewhere. And we see how that's pretty consistent here, right? If we think of this as a local maximum, where it's concave down, and this is a local minimum, where it's concave up, the natural way to connect these is with something sort of like, this is wobblier than it should be because of my tablet. Again, my apologies. That should be not perfectly straight, but a good bit straighter than that. On this side, it'll come up. On this side, it'll come down. And this will be our main features here. We didn't really talk about end behavior. I don't think that was listed in the main list, but it might be worth considering. You know, in past classes and also earlier in this class, you talked about end behavior of things like this, and we can tell that this x to the 5th is going to dominate. So if x approaches positive infinity, well, let me phrase it this way. From past classes, like in a pre-calc, for instance, you would look at this and say, okay, as x approaches positive infinity, with this x to the 5th dominating, this y would approach positive infinity. As x approaches negative infinity, y approaches negative infinity, because this is odd here. So we have approaching positive infinity to the right, negative infinity to the left. If we wanted to be a bit more precise with our analysis, we know now, if we're considering x approaching positive or negative infinity, this is an indeterminate form, infinity minus infinity. We saw that in the section on L'Hopital's rule. And to work with that a bit, we might want to factor it. So if we look at this factorization, now we can see, okay, whether x is approaching positive or negative infinity, the second factor is approaching positive infinity. So then it's just a matter of what this is doing. When x approaches positive infinity, the product approaches positive infinity. When x approaches negative infinity, the product approaches negative infinity. So having that factored form can make it a little bit easier to identify the end behavior in a rigorous sense. Again, with polynomials, we kind of have a sense of how those go based on the leading term. But many of the functions you will deal with are not polynomials. So sometimes, if you're trying to figure out the end behavior, that sort of factorization could be very useful. Now, there's a little bit of thought as to why we went through all this effort to get a relatively simple graph here, and also comparing it to thinking about the use of graphing calculators in computers. You know from experience that you can get a graph like this pretty quickly by just throwing this into a graphing calculator or asking a computer to graph it. But you also hopefully know from past classes that a 5th degree polynomial can have up to 4 local extrema, what they might have called turning points before, and could have up to 5 zeros. Here we've only found 2 extrema and 3 zeros. So if you graph this, and you know enough about 5th degree polynomials to know those facts, you might look at that graph and think, okay, well, that's great and all, but is there anything else? Right? Is this a complete picture? Because I only have 3 zeros and 2 turning points. There could be more. And yes, if you know more about things like Descartes' rule of signs or the upper and lower bound theorems, you could analyze this and figure out that no, this is all that we have. But depending on how thorough your pre-calc class was, you may or may not have talked about those things. I don't think we usually delve into that much in our current curriculum, although the college algebra course or algebra for calculus, that might be a bit more thorough and talk about those. It's been a while since I've taught that, so I'm not sure what all is in its curriculum these days. So depending on what classes you had in the past, you may or may not have the tools to be sure that this is everything. But a little bit of calculus allows us to quickly identify that no, these are the only extrema. That didn't actually take too much work in this case. A little bit of factoring, and we could easily see that these are the only zeros. So we can be confident that this is a complete picture of the graph. Again, this is more wobbly than it should be in the middle. You can use a computer or graphing calculator to get a more accurate graph that is going to be a much cleaner and smoother curve. Polynomials usually behave quite nicely. But this is just a demonstration of walking through those various points with a relatively simple function and looking at how we can apply and interpret all of those.